All right, so what we did last time with these is we looked at some partial sums, and when we tried to, essentially see if we could recognize any kind of a pattern with those partial sums. Last time, didn't the partial sums seem to be converging towards a sum of 1? Is that right? I forget, and it's on the other page. Is that right? So we're headed towards a sum of 1. With number 2, I think we're going to find something pretty different happening. Let's go ahead and do S2, and then I'll have you guys do S4 and S6. S2 is the partial sum based on n being 2. So when n is 1, that term would be 1. So let's see here. So S2 would equal, the first term would be 1, the second term would be 2. So let's see here. 1 plus 2 equals 3. So my S2 is 3. So let's see if you guys can do your S4 and your S6. And we'll try to draw a conclusion about that, whether this series seems to converge or diverge, or any other pattern we can kind of see. Oops, that's not what I wanted to do at all. What do you guys have for S4? 10? Okay, yep. Well, here, let's figure that out. So it'd be 3 plus, and then we'd have to add the 3 and a 4 to that, right? So plus 3 plus 4 would give us 10. And then how about S6? That would be 10 plus 5 plus 6, right? So do you guys get 21? Okay. So I don't know if this is enough for you guys to see a pattern here, but the question next, we can do more if you want. The question next says, does this series seem to converge? Converge means like narrow in on an answer, right? An actual numerical answer. Or does it seem to diverge? And diverge is code word for, does this thing seem to be headed towards infinity? What do you see? Diverge, right? I mean, if you think about it, aren't, like if we did like S8, S10, S20, S300, aren't the numbers that we're adding to the previous numbers just going to get bigger and bigger and bigger and bigger? And so definitely going to be a diverging pattern to where, you know, we would say that the sum would be heading towards infinity, so there isn't a real answer to this. Whereas in number 1, there was an answer we seem to be heading towards, and that was 1. So anyway, we will do partial sums, maybe more than you think. We'll do quite a bit of them. This is just kind of some basics with that. Let's go ahead and flip over to the next page. We'll do a little bit of work with this, and that'll be it. So the point there at the top, like if our goal was to decide whether a series converges or diverges, and maybe to a certain number, and our method was always to compute those partial sums. Like let's do S2, S3, S4, S10, S20. Like at very best, that's going to take forever, right? And at worst, it's going to be really difficult to tell. I'm going to point out a couple of series as we go where partial sums would probably be a little deceptive. Like you'd think, yeah, it's going to do this when it really does something else. So instead of like computing a bunch of partial sums and have you guys turn into just like adding things up, sort of, that's all we do. We're going to be a little more efficient. We're going to use some tests to determine convergence or divergence. And I use the word vital. You guys know the vital is the root word in vitality, which means life. So if you want to have life in this chapter, right? If you want to have life in this chapter, you need to have these things as mastered as possible. That means, as I explain these, if that makes perfect sense to you, great. If it doesn't, you need to ask. Okay, why this? Why not that? And I think if we are all working towards that same goal, I think we'll be in pretty good shape. But there's quite a few tests. I'm not going to lie to you. That's why we're going to take 6.5 weeks with this chapter. We're not going to go too fast, but there's plenty to do. Okay, so the other thing is I want to give you guys kind of a framework, sort of a reference frame for how we're going to look at these different series. We're going to look at lots of different series. And here's going to be kind of our general framework. And this is just my thing. It's a little silly, but I hope that it makes sense to you. So as we look at these series, more or less, for the most part, the question is going to be, does this series converge or diverge? Sometimes we'll be able to say, hey, this series converges, and the answer would be this. We'd be able to actually figure out what that sum would be. Other times we're not going to be able to figure out what the sum is, but we can say, well, there is a sum, because we know this converges, or we're going to say there is no sum because this series diverges. So here's my conventional way to think about this. I want to think of us as like cheering for the series to converge, right? Because it's a little weird to say, hey, there's a series of numbers added up and there is no real answer, right? So it's like, almost feels like you lost. That's not really true, but just our way of thinking. Let's say we want to be cheering for these little series. Come on, you can converge, you can converge. And sometimes they disappoint us and they diverge, right? That makes sense? So let's come at it from that perspective. We want them to converge, but we're going to be honest about this. And so from that perspective, I want to share two tests with you. The first one is, and there's more than just these two, but the first two tests are this. The nth term test. So the nth term test, I would say, is a highly negative test. So I don't know if you guys, how many of you are athletes or have been involved with the arts or something like this, but many of us that have had coaches, for whatever, have had this type of coach. Listen up. Have you ever had the type of coach that only seems to say something when you do something wrong? You know what I'm talking about? So like there are some coaches where you do something great and you execute the skill or the play or the whatever perfectly, and the coach just is kind of like, whoop-de-doo, right? They don't really say anything. But the minute you mess up, they're all over you, right? They get upset. And it's kind of tough to play with that all the time, right? I mean, I think everyone kind of has their breaking point, but after a while, I think you get kind of sick of that, right? Where the only thing you hear coming out of the coach's mouth is, you messed up. That's not right. So we need to hear that from time to time. But if that's all you hear, it's kind of tough, right? Yes? Okay. That's what this nth term test is. Okay? The nth term test, if the series is headed towards convergence, the nth term test will be silent. It won't tell us anything at all. But if the series is headed towards divergence, the nth term test will be the first one to call it out. Okay? Make sense? So here's the nth term test. It's based on limit as n goes to infinity. So it says if the limit as n goes to infinity, and then a sub n stands for the general term of the series. So if you go limit as n goes to infinity of that general term, and you get something other than 0, anything, you get anything other than 0, the series diverges. I want you to think about that for a second, why that is. If you do the limit as n goes to infinity of the nth term, and you get something other than 0, doesn't that mean at the very end when you're going plus this, plus that, plus something else, plus whatever, if you're not headed towards 0, aren't those like last numbers? I mean, I use that term loosely, right? Aren't those numbers way out at the end going to be non-zeros? So you're going to continue to add non-zeros to it. It's just going to get bigger and bigger and bigger, getting closer to infinity, right? So if you do this limit as n goes to infinity of that nth term and you get anything other than 0, then the series diverges. You, however, cannot turn this around. You can't say, oh, well, if the terms do head towards 0, then the series converges. You can't say that. It doesn't work that way. Show you one primary counterpoint to that thought. And so this test, the nth term test, can only say that a series diverges. Okay? So you can never say, this series converges due to me doing the nth term test. You simply can't say that. It doesn't prove that. Remember the nth term test, you can think of the nth term test almost like a referee in a game. Right? I mean, when was the last time a referee blows their whistle, stops the game and be like, excellent layup, Tess. All right, play on. No. The only time a referee blows their whistle is to say, sorry you traveled. Right? They only call things on you that negatively affect, right? One exception, I suppose, would be a charging call, but I mean, you could look at that from both perspectives. But typically, the referees only call something, they only blow their whistle when there's like a penalty to be assessed. That make sense? So anyway, you can think of the nth term test kind of like that. And then the other one here, I'm hoping that you guys remember this from, like a pre-calc class, the geometric series test. So geometric series, I find that one of the harder things with the geometric series is to keep in mind what it actually looks like. So the geometric series is anything of this form right here where you start off with the first term and then each time to get the next term you multiply by some common ratio. So that's the one we looked at in number 1 the last time I saw you guys, or the time before that I guess. I think we multiplied by 1/2 each time. So you get the next term, you multiply by 1/2. Get the term after that, you multiply by 1/2 again. So A is what we call the first term, R is what we call the common ratio. And the geometric series with that common ratio of R, it diverges if the absolute value of R is bigger than or equal to 1. Let's think about why that is. Like if your common ratio is say like 3, doesn't that mean that to get the next successive term you multiply by 3? So like a geometric series in that sense would be like 1, 3, 9, 27, 81, 243, ... And so the numbers are just getting huger and huger. You're clearly going to be diverging towards infinity, right? However, if the common ratio's absolute value is between 0 and 1, so what numbers are between 0 and 1? What? Well, yeah, but what kind of numbers? Decimals, fractions, right? We'll typically look at these like as fractions. Then the series converges, and we can actually not only say that the series converges, it converges to A over 1 minus R. Again, keeping in mind that A is the first term, and R is the common ratio. Okay, so we're going to build up a whole library of tests in your brain. We're going to try to connect them, and if you look way ahead, like I think it's after section 9.6, there's a little flow chart as far as how these tests will work as you try to test different series. So we're going to start off with these two, and we'll build up others. And I think we'll do maybe like 1 or 2 examples here real quick before we move on. So do you guys have any questions here? We kind of have to do a few questions for you to maybe understand if you need to ask questions, so maybe we should do that. But let's go ahead and flip ahead to our next little set here, and then we'll call it good. Okay, so with 1 and 2, take a look here. Sigma from n equals 0 to infinity of 2 to the n. Now you really only have 2 series tests to work with here, and I suggest that this might be sort of impractical, but I suggest that at the very least you think about the nth term test first, because the nth term test is very conclusive on one thing. Like if the series is going to diverge, it'll tell you that immediately, right? And if it doesn't tell us anything, then we move on to other stuff. So we should at least consider this. And I find, just a personal note for my own self, I find myself as I look at questions like this, as I do some questions like in some test prep book or the newest AP test or whatever, I always find myself forgetting about the nth term test. I don't know why. I just like jump to these other ones that you'll find later. And so that's just my own issue. I hope that you guys don't share that with me. But let's go ahead and consider this. Take a look at your nth term in there. It's 2 to the n. And so I'm just going to say, I'm going to try this out. Limit as n goes to infinity of 2 to the n. I'm going to use this nth term test. So, the nth term test, as you do this, limit as n goes to infinity, what number does it give us? Infinity, right? 2 to some power increasing without bound. You're going to get an infinite quantity there, if you will. So yeah, infinity. And so what is the most important thing about infinity in this case?
It's not 0.
It's not 0. Yeah, that's exactly right. So we can say not equal to 0, and so we can come to a conclusion right now. Because the nth term is not heading towards 0, we can say something like this. Because, well, let's see here. I'll repeat myself a little bit. This is probably a bit much. But because the limit is n goes to infinity of 2 to the n doesn't equal 0, the series diverges. I want you guys to get into the habit of doing this at this point and writing out the test that you used to come up with your answer. So series diverges due to the nth term test. That make sense? What if, though, you were doing a question like this, and I don't know, maybe you're like me a little bit, and the nth term test, for whatever reason, did not occur to you right away, as far as that's what you could use. What if you use the only other test available to you right now? And that would be the geometric series test. Okay, so the first thing you want to do is look at the nth term and ask yourself, is it a geometric series? Is it truly some number, and then to get the next term, you multiply by a common ratio, and then to get the term after that, you multiply by another common ratio? Is it truly a geometric series?
Yeah.
If it is, what's the common ratio?
2/5.
Say again?
2.
You've moved on to number 2. I'm still doing number 1.
Oh.
So in number 1, what's the common ratio?
2.
2, right? So if you think about 2 to the n, like maybe if we did a partial sum and listed out some of the sums, or some of the terms here, maybe we could write equals, what would be your very first term? If n is 0, 1, plus, just go,
2.
plus,
4.
Allie's got it, plus
8.
8, plus, so on and so forth. You can see that each time the term is just doubling, right? Times 2, times 2, times 2. And so that's a characteristic of a geometric series. I would say that a geometric series should always have some kind of a numerical base and a variable exponent. Something to think about. Okay, so then if the common ratio is 2, like we said, I'm going to say r equals 2. So therefore we can say that the absolute value of r is greater than or equal to 1, right? 1 is the most important number there with the geometric series. So if the common ratio is bigger than 1, can we say then this geometric series converges or diverges? Diverges, yeah. So we can say something like this. You can write GST for geometric series test. So by the GST, the series diverges. So from a grading perspective, I'm going to want to see that you have essentially analyzed R, that you've told me what R is and how it relates to the geometric series test. Excuse me. And then a conclusion. Series diverges. So, just like the nth term test is like the referee or the really rough coach that only tells you bad stuff, the geometric series test is a little more balanced, right? Geometric series will tell the series, yep, some of you converge and some of you diverge. It's not all about being negative. It's not all about being positive. It's about being balanced. So I'd say the geometric series test would maybe have a good perspective. Does that make sense? I'll be able to tell you both. Depending on what the series is, it'll work. If the series is not a geometric series, you can't use it. So anyway, that's that. Take a look at number 2 real quick. Number 2, you've got to work with some fractions a little bit. If you notice, it does have some variable base or some variable exponents on numerical bases. I'm just going to manipulate this a little bit for you guys. What I would do is this. If I wanted to really see this clearly, I would go sigma as n goes to 0 to infinity. I would rewrite this to be 2 to the n over 5 to the n times 5 to the 2. Remember, if you are adding your exponents, you're really multiplying your bases. And then I think because that second 5, the 5 to the 2, doesn't have an n with it, I can essentially factor it out of the sigma. So I'm going to write it as 1/25 sigma from 0 to infinity of 2 to the n over 5 to the n. And then perhaps one more thing you could do to make this a little more clear would be to write it like this. 1/25 sigma from 0 to infinity of 2/5 to the n. Does that make sense, right? Because if you wanted to go back the other way, you just say, well, the n applies to both the 2 and the 5 as an exponent. Okay, so we do all that. Sometimes that'll be pretty nice to do, pretty important to do. We do all that and get to this point here and say, all right, what kind of series is this? It's geometric because, again, the characteristic there is just a numerical base, like 2 or 2/5 or whatever, and then a variable exponent. That should always lead us to a geometric series. So, in order to decide whether this series converges or diverges, we could do the nth term test. Check this out. We could say limit as n goes to infinity of 2/5 to the n. So as you think about these partial sums, it would be 2/5 times 2/5 times 2/5 times 2/5 times 2/5, right? So would it be fair to say that the denominator is going to get huger faster than the numerator. Let's think about these terms of do. We start off at 0, it would be 1 2/5, 4 25ths, 8 125ths, right? 16 625ths. Aren't those nth terms headed towards 0? You see that? So I think we could say this equals 0, but here's where the nth term test sort of lets us down. Instead of us being able to say, and therefore the series converges, what are we going to say? Nothing. We still don't know. We really don't. We might think we do, and if we know about the geometric series test, we actually can make a conclusion here pretty quick. But based on what we've done so far with the nth term test, we don't know. So not that you'd have to write this, but you could say nth term is silent, right? It doesn't give us anything to conclude based on that test.
Just a question.
Yeah.
It seems like it's quicker to just use the geometric
It is.
series.
It is. So what I'm trying to do here by showing you the nth term test for this is to say, don't forget it.
Okay.
I'm trying to like solidify it a little more in your brain,
Okay.
and maybe my brain too, that always consider this, right? And I agree with you that the nth term test really does not need to be considered here. If you recognize it's geometric, then you should be able to jump right to that. That's fine. But I thought I'd show it to you.
Good.
Yeah. I just wanted to show you an example of where the geometric series, the nth term test is silent.
Okay.
It tells us nothing. Okay, so we do use the geometric series test as test suggested. And so what is our common ratio? 2/5. And so we can say then that
Is that not 2/25?
just 2/5. The 1/25 we pulled out. So 0 is less than or equal to 2/5, which is less than, or no, excuse me, less than 2/5, which is less than 1. And so we can say then by the geometric series test, the series converges. And because we actually have a formula for this, we could actually find out what it converges to. Here's that formula from above. We didn't have to do this, but we could do this. It's first term, and the first term here would be, depending on how you look, head on out. Oops.